When it comes to calculating relative velocity when you have two different frames of reference, it can be a little bit trickier, but you can solve it either thinking about it logically or applying a mathematical equation. I'll explain both. I recommend the mathematical equation because in some cases it's harder to kind of visualize, and I think the methodology behind the equation kind of makes sense. It's a little bit like a puzzle, but you can decide which method works for you. So let's jump into an example first. So similar to the last examples, you have a train moving, but you have student A, student B, and I'm going to call this ball C, just so we have A, B, and C. The train, and therefore everything inside of it, are originally traveling at 40 meters per second north relative to the ground. So that means if you stuck your head out the window and looked down, the ground would appear to be traveling south at 40 meters per second because you are traveling 40 meters per second north. While that's happening, student A throws the ball with 6 meters per second north of velocity, but not relative to the ground, relative to the train towards student B. So if we want to figure this out, we have a little bit of a situation here because in our previous example, which was the one-dimensional, both of these was related to the ground. So you had the same frame of reference. Here we have a different frame of reference. One of them is the ground, or the earth, and the other is the train. So how do I rectify this? Well, you could do two things. Logically, if you think about it, before the ball was moving, before the ball was thrown, it was moving at 40 meters per second north relative to the ground because that's how fast everything in the train was moving. When it was thrown with 6 meters per second north of velocity relative to the train, which was already moving at 40 meters per second. So if I added 6 meters per second in the same direction, this should just come out to 46 meters per second north. This one's a little bit straightforward, but it gets a little bit trickier if I don't ask you relative to the ground. If I were to say, what is the speed of the ball relative to the person or relative to someone on another moving train or something, that'll get a bit tricky. So let me show you kind of the mathematics behind it, and I'm going to try and explain this as best I can. But I first listed everything that was given in the problem, and I just want to explain what this notation means. This is the velocity of t for the train, the velocity of the train relative to the ground, the velocity of student A relative to the ground, the velocity of student B relative to the ground. So in relation to the ground, the train and everything in it is moving at 40 meters per second, which is where this came from. And the velocity of ball C relative to the train was 6 meters per second north, which was taken from here. So if I just list all of those, now the equation becomes a game of, can I get the right letters in the right order? And here's what I mean by this. If I'm being asked to find the velocity of the ball C, relative to the ground, then I'm really looking for V, C, G, the velocity of ball C relative to the ground. Now, if I look over here, I don't have that anywhere. I don't have the velocity of the ball relative to the ground at all. So what I need to do is I need to find what's called an intermediate frame of reference or a common frame of reference. In this case, I want to connect C, the ball, with G, the ground. And technically, I do have something that has C in it, and I do have a bunch of things that have G in it. So then I say to myself, well, is there a common frame of reference? And in this case, well, the velocity of C is in relation to the train. I have the velocity of the train relative to the ground, so I can kind of form a connection here, C to T, and then from T to G. And that's what I did over here. Instead of subtracting, so when you had the same frame of reference, you subtracted. In this case, when you have different frame of references, you are going to add. And you need to add in such a way, so if I'm looking for the velocity of ball C relative to G, if you look at the two that I'm adding, the outside of each are the letters I'm looking for. So C and G are on the outside. If I'm looking at 1, 2, 3, 4, the C, T, T, G. C is on the outside left. G is on the outside right, which is where I get CG. And then the two inside letters must be the same, must be that common frame of reference. So if you think, this isn't the way to think about it, but if you almost think, well, the T cancels out because it's in the middle, that leaves VC and VG, which is exactly what I'm looking for. So I do have the velocity of the ball, C, relative to the train, which is 6, so I made it positive, plus, remember we add in this case, the velocity of the train relative to the ground, which was 40. Since it's north, it'll be positive. And as we thought logically about before, you wind up with 46 meters per second north, because the 6 meters per second was basically just added on top of the 40. The way to think about this, I guess if I'm trying to break it down easier, is if you want to find the relative velocity when you have different frames of reference. I made this one up, but if you want the velocity of A relative to C, well, you have to add two velocities, and the outside letters must be the desired frame of reference. So in this case, A relative to C, so A relative to C, and I can only add these two if they have a common frame of reference internally. So when you're adding these two, it always has to be the letter you want that comes first, two similar letters that you're not looking for, and then the last letter has to be the letter that you want to find. Give this one a shot, and you can pause the video when you're done and pause the video, solve the problem, unpause it, and see if you did it correctly. Again, any questions, please let me know. This stuff can be a little bit tricky until you see it, and then it kind of becomes second nature.